The next category of reactions we're going to look at is something known as a single replacement reaction. Now, a single replacement reaction is something that involves an element replacing one part of a compound. In a single replacement reaction, the products will include what's called the displaced element, or the one replaced from the compound, and whatever the new compound is that's formed. The identifying feature of a single replacement reaction is we're going to have an element reacting with a compound. The element's going to come in and trade places with one of the atoms that are in the compound. The element will turn into an ion, and the ion in the compound turns into an element. So what we can see in a single replacement is we have this element A that's going to replace B in the compound. B turns into an element, and A now becomes part of the compound, replacing B in that compound. Hence the name single replacement. In a single replacement reaction, an element can only replace an element in a compound that is less active than itself. To figure out how this works, we need to use a tool that's known as the activity series, which indicates which elements are more active than other elements. Now then, to our left here, this is something that's known as the activity series. And this will be used to figure out which single replacement reactions happen and which ones don't. Now the first part of this, let's take a look at this part here. The guideline here is that a metal in elemental form that appears above another metal that's in ionic form will replace that lower metal that's in a compound. Let's do an example to show exactly what this means. Here's our example reaction. We have zinc reacting with copper 2 nitrate. The zinc is in its elemental form. This is an element. Copper 2 nitrate, this compound, is made up of copper 2 plus ions and a couple nitrate ions. So in our compound, the copper 2 plus is an ion. Now what will happen in a single replacement reaction is the element and ion will trade places, only if the element is higher up in the activity series than the ion. Looking at the activity series, we want to find both zinc and copper. Here we have zinc, and here we have copper. In this particular circumstance, our element in the reaction, which is elemental zinc, is higher up in the activity series than our ion in the reaction, which is the copper 2 plus ion. In this circumstance, in which the element is higher than the ion that it's going to react with in the chemical reaction, this means that a reaction will occur. And we're going to have the element trade places with the ion in our single replacement reaction. So what will happen in our single replacement is our element is going to displace or replace the ion in our compound. The element will turn into an ion, and the ion will turn into an element. So what we're going to make here is elemental copper will be one of our products, and then the new compound is going to be zinc nitrate. To determine the formula of our compound, we have to identify our charges. Zinc is 2 plus, nitrate is 1 minus, so the formula would be Zn with 2 nitrates combined with it, NO32, and this will now be aqueous. And that would be our single replacement reaction. Inspecting the reaction, it's balanced as is, so this would be our single replacement reaction for a metal, zinc in this case, replacing an ion, copper 2 plus, in a compound, which would be an example of a single replacement reaction. Now, not all single replacement reactions occur. If the element in the activity series is lower on the activity series than the ionic form in the compound, no reaction will occur. Let's do an example. Okay, here's our reaction. We have elemental silver reacting with an aqueous solution of nickel 2 nitrate. In the reaction, our silver is the element. The nickel 2 plus is our ion in the nickel 2 nitrate compound. Let's take a look at the activity series. Here we have nickel, and here we have silver. In this circumstance, our ion, the nickel, which is the ion in our reaction, is higher on the activity series than the element in our reaction. In this circumstance, when we have the ion higher than the element, that'd be the circumstance when we have no reaction taking place. All we'd have is some elemental silver that gets wet in a nickel nitrate solution, but nothing changes places and none of the compounds nor elements change. Now, the first two examples have looked at elements that are metallic replacing ionics that are metals, metal ions. This can also take place with nonmetals. If we have a nonmetal in its elemental form, it'll replace the ion in a compound, but it's specifically going to replace whatever is the nonmetal ion in that compound. For example, we could have this reaction with elemental fluorine reacting with an aqueous solution of sodium bromide. Now in this circumstance, because our element is a nonmetal, it'll replace whatever is the nonmetal in the compound. In this case, bromide ions are our nonmetal, and that's going to be the ion that would get replaced in this reaction. Now there's a second part on the activity series that focuses specifically on nonmetals, so we still need to check, is the element higher up than the ion in the activity series to see if the reaction will occur or not. In this case, looking for fluorine, we find that fluorine is higher up than bromide in the activity series. Because we see the element is higher than the ion that will get replaced in the reaction, this would be that yes, then a reaction does occur. What's going to happen is our element is going to replace the ion and turn into an ion, and the ion turns into an element. So what we're going to make here is elemental bromine, which is Br2 because it's in the Hunkelbrief series, and then we're going to make sodium fluoride. Now sodium is 1 plus, fluoride is 1 minus, so the formula of the compound sodium fluoride would be NaF, which is now aqueous. Now to balance our equation, we need to put a 2 in front of the sodium bromide and a 2 in front of the sodium fluoride, and this would be an example of a single replacement reaction where the element is a nonmetal and it replaces a nonmetal in a compound. Let's take a moment now and examine hydrogen in single replacement reactions. Hydrogen has some special categories. For example, the metals on top here in the activity series can replace hydrogen out of water. It's just at room temperature. We then, as we move down and get a little less active, these react with acids or hot water, steam, but will not replace liquid water, hydrogen in liquid water. A little bit further down with less activity, we have metals that replace hydrogen from acids, but not water. And eventually we get down to some metals that are just unreactive with hydrogen in all circumstances. We'll do an example with the first one to start. This will be our reaction. We have an element, lithium, reacting with a compound, water. So this would be an example of a single replacement reaction. When we look at our activity series, we see lithium is very high in the activity series, and that's our element. And it says that these elements react with cold water and acids to replace hydrogen from the compound. Now, one thing we can do just for purposes of looking at this reaction is we have lithium, it's a solid, and let's rewrite water as HOH. What's going to happen here is the lithium is going to replace only one of the hydrogens in the compound. The lithium is going to turn into will turn into ionic lithium, and this hydrogen that gets replaced out of the water will turn into elemental hydrogen. Now hydrogen, being of the Hunkelbrief series, when this gets replaced it turns into H2. Lithium is 1 plus in its ionic form. OH, which is remaining after the one hydrogen gets replaced from the water, is OH 1 minus. So the other compound that gets formed here is lithium hydroxide, now in the aqueous form because it would be dissolved in the water. Writing a 2 in front of the lithium hydroxide and a 2 in front of the elemental lithium would now balance our equation, and this would be an example of a single replacement reaction where we have an elemental metal replacing hydrogen from water. Now another skill we're going to add to our chemistry repertoire is how to write something called a net ionic equation, which comes into play with single replacement reactions. Earlier, an example we had of a successful single replacement reaction, we use this reaction where elemental zinc react with copper 2 nitrate to make elemental copper and zinc nitrate aqueous solution. This equation is referred to as the overall balanced equation. Now the first step we're going to take represent the aqueous solutions as they would actually appear in the container, or what would you actually see if you went for a swim in the solution? We wouldn't see any copper nitrate stuck together, but when it says aqueous, this actually means we have copper ions, and they separate when they dissolve from the nitrate ions. This would be an electrolyte, so we make copper ions and nitrate ions that are separate in solution, and that's actually what's in the solution when we say something is aqueous. We're going to rewrite the equation representing the aqueous solutions as they actually appear in solution, with the copper 2 plus ions aqueous separate from the 2 nitrate ions, and likewise the zinc 2 plus aqueous ions being separate when they dissolve from the 2 nitrate ions. The purpose of this process is actually to simplify our balanced equation. Now in this reaction, we have a chunk of solid elemental zinc placed in a solution with copper ions and nitrate ions. And this is how this would look before a reaction takes place. Now, after the reaction has been completed, what we would now see in solution is we'd have some elemental copper, we'd have zinc ions that are now aqueous, and we'd have nitrate ions. Now, what we want to do is identify what things have actually changed chemically and what things have done nothing. Well, if we look, our zinc and copper have traded places, where the zinc started as an element, the copper as an ion, and they've finished now as copper is now an element and zinc is an ion. They've undergone a chemical change. Continuing to examine our containers, we can also see that the nitrate ions are aqueous as reactants, and we have aqueous nitrate ions as products. The nitrate ions have done absolutely nothing. Ions, in this case, that do absolutely nothing in a reaction are known as spectator ions. Essentially, they've just been watching what's going on in the beaker without actually participating. The next step in our process is we're going to eliminate any spectator ions from our chemical equation to simplify the reaction. Because we've identified that the nitrate ions are spectator ions, in our reaction we're going to take the nitrate ions and eliminate them, because they've done absolutely nothing chemically. Once removing the spectator ions, we now have a reaction that represents and shows only the actual chemicals that are changing as a part of the chemical process. The nitrate ions have been eliminated because they did nothing and remained unchanged in the reaction. This now simplified version of our balanced equation is known as a net ionic equation, and it shows only the chemicals that actually undergo a chemical change in the chemical reaction. All spectators, or ions that do nothing and remain unchanged between reactant and product, have been eliminated.